And let me share the screen. So here's our implicit function theorem, right? So let me kind of briefly go over it. Okay, so you have a system of n equations. F1, which is a function of x1 through xn. And the nth, so this is equal to 0. And this is a system of equations we have, right? And of course, there are these functions have these parameters. So, so for a given value of parameters, there are solutions, right? For a given vector of parameters, each ith variable will take this value, right? So this is the solution to the system of equations, all right? So if we write it in that form, if we insert the solution values, then all of these become identities. Yes. So now we can differentiate each of these equations with respect to A and equate the two sides. Yeah. So start with the first equation. If we differentiate with respect to A, we get del F1 del X1 times this derivative plus del F1 del X2 and this derivative, and so on, del F1 del Xn times this derivative equals 0, right? And the very last one, so we can proceed like this. The last one will be del Fn, the nth function, differentiated. Sorry. I missed one term. When I'm differentiating with respect to A has itself affects the value of the function, right? So at the end, I missed out one term, which is del F1 del A. And if I take it to the other side, that will become minus del F1 del A. Okay. And then as we move to the last equation, del Fn del Xn equal to minus del Fn del A, right? So now we are interested in these derivatives, and we have another set of n equations. right? And what are we interested in? We are interested in each of these. These are our comparative static derivatives, right? X1 prime A, X2 prime A, and so on. Now, if you look at this closely, we can write it in matrix form. In each of these lines, there's x1 prime A, x2 prime A, etc. They're all linear functions of these derivatives with different coefficients, right? So the above set of equations is equivalent to del f1 del x1 del f1 del xn del fn del x1 and del fn del xn, right? That multiplied by the vector of the derivatives we are interested in. Equals this vector minus del f1a all the way down to minus del fn del a, right? So this is just rewritten. Now, if you look at this, this is indeed the Jacobian matrix. Okay? So, in linear algebra, we know how to solve this kind of set of linear equations, right? We use something called Cramer's rule. C or K, I forget. C. Okay. So for the ith derivative here, let's say x I prime a, standard solution techniques from linear algebra tell us that it is given by this matrix, its determinant in the denominator. So determinant of the Jacobian matrix. And in the numerator, we calculate another determinant, which is the Jacobian matrix, where the ith column is substituted by this column. Yes, the ith column here. That's what Cramer's rule tells us, right? So it's a straightforward application of Cramer's rule. So this ith column has to be replaced by this, and then we calculate the so let's call that matrix Ji, yes, and we calculate the determinant of that. So that ratio is the solution. Yes. So, the implicit function theorem, what we wrote down sort of follows quite simply using a little bit of linear algebra. And, in those simple examples, I was trying to sort of drive home the point that once you take an equation that defines your model and you plug in the solution, it becomes an identity, and that gives us this sort of a technique to carry out these comparative statics exercises. That's exactly what we have done here, as you can see, right? We have done it for a more complex case of several equations.
Sir?
Yes.
Sir, in the right-hand side of the equation, sir, how did we get minus del f1 upon del a or minus del fn upon del a?
I mean, look at the first equation, okay? We are differentiating it with respect to A. A is one of the, I initially sort of skipped it, but I mean, it's of this form. So equation I, or let's say equation J, is of the form, it's a function, rather identity J is of the form x1, it's a function of A, x2, a function of A, xn as a function of A, and the function itself is also a function of A. So now just take derivatives, right? I mean, it's this straightforward differentiation. So that derivative, if you take differentiate with respect to A, the last term you will get is del Fj del A, and the first several terms is as I wrote down. All of that equal to 0, so you take this to the other side, it becomes negative.
Okay, sir.
Sir,
Yeah,
sir, in this analysis, the implicit function theorem, we mentioned that there are m parameters A, uh, which are A. Then why are we specifying that there are m parameters when we're just looking at one particular A?
I just showed you the proof for one parameter. So, right, in this case, because it
Oh.
didn't want to write down too many subscripts and all, right? If there's a whole bunch of parameters and I'm taking derivatives with respect to one of them for that exercise, I can forget the others.
All right, and then we do this for the rest of the
Or
m
any
minus 1.
other parameter, exactly the same analysis. Yeah.
Oh, all right. All right. Thank you, sir.
Yeah. All right, so let me move ahead. I'm way behind, so I'll have to speed up a little. Um, okay, so we've talked about properties of the um, indirect utility function and so on. So today let's start with duality theory. And as I said, we'll talk about a whole bunch of things, results, this, that, but all of that is leading up to the question, the most important question, what are the testable implications of this sort of theory, if any, right? If the theory doesn't give us any testable implications means that the theory predicts something which can be put against observable data, right? A theory which says, if something happens in the market, prices go up, incomes go down, whatever, then consumers have higher utility. That's not a testable implication or prediction of the theory because we can't look inside consumers' heads and see what's happening to their utility. We can measure prices, we can measure incomes, but we cannot measure utility, whatever that is. So that's why we want to sort of build up the theory to a point where the theory says something about the world, about the economic world, which we can go and collect some data, at least in principle, and find out whether what the theory is saying is borne out in the data or not, right? So that will make it a falsifiable theory. Now, if the data contradicts the theory, then we have to throw it out, yeah? But if the data is consistent with the theory, what the theory's predictions are, then the theory has survived. Then the theory doesn't sort of get a free pass till the end of time, but for now, the theory has survived and our confidence in the theory has grown to some extent. So that's where we are trying to go, right? Okay, so let's talk about duality. Maybe I should keep it like this. Okay. So let's go back to our consumers problem. So in the consumers problem, there's a fixed income or budget, and the consumer is trying to get to the highest indifference curve. So let's say the consumer's income takes that value Y1. Okay. So this budget line is for the income level Y1. And for that income, the optimal amounts are x11 and x21. Okay, and this is the point of tangency A. Okay, and once we find the point of tangency and we look at the indifference curve there and look at its utility level, let's say we find that the utility level is U1. Okay, actually, let me, just not so that not to confuse, let me make these subscripts zeros. All right, so we start with Y0 amount of income. The optimum point is tangency A, tangency at A. X10, X20 are the optimal choices. U0 is the utility level attained through utility maximization. And this problem, this picture pertains to the utility maximization problem. Max UX subject to y minus px equals 0. Okay. Now, think of a different problem where there's no fixed budget, right? But there's a target level of utility. All right. So if you want a story to go with it, think of the government trying to help the poor, and the government has decided that the poor has to be given resources or income or aid so that they get to a certain desired level of utility that is deemed socially desirable. And so the question for the government is, how much money should that poor household be given? Suppose the household has no income. So how much money has to be given so that the target level of utility can be achieved by the household, right? So that problem takes the following form. The problem I just described, it takes the form minimize px subject to ux no less than some target level u bar, right? So what's the difference between these two problems? Basically, the objective function and the constraint functions have switched position. Yes. This problem, I can also make it equality constraints, right? If you're trying to save money, then you don't want to overshoot the mark, right? You don't want to go to a higher level of utility than is necessary. So we can describe the problem as inequality constraints, but very quickly we can replace it by an equality constraint and the solution will be the same. All right. So so what's the link between these two problems? This first problem's objective function is this problem's constraint function, and the first problem's constraint function becomes this problem's, so let me write it as px equals y. Yes. The left-hand side of the constraint becomes the objective function in this problem. So these are called dual problems. They are like, mirror images of each other. Okay. Now, if you think about this problem in the simple case of two goods, what's the nature of the problem? You have a fixed indifference curve. So a point has to be chosen on the indifference curve, not on the budget line. And instead of a fixed budget line, you have a series of what may be called isocost lines, right? Lines like this. Each line is derived from a certain level of the budget, a certain level of expenditure, right? You increase the level of expenditure, you move to a higher isocost line. All the isocost lines, of course, have the slope of minus P1 by P2, okay? So in this problem, we are trying to reach the lowest isocost line without moving away from this indifference curve, right? So we have to stay on the indifference curve, but we want to choose a point on the indifference curve which lies on the lowest isocost line. And the same logic as before tells us that, if I choose a point like this on the isocost line, then I can easily move to a point like this, and that will lie on a lower isocost line. So this can't be optimum. So the optimum point will be a point of tangency. So the dual problem of the consumer's problem, right? This is utility maximization, expenditure minimization. These are the two dual problems. So the dual of utility maximization is also characterized by a tangency condition. Okay. Now, there's a further link between the two problems, and let me get to that. Go back to the consumer's problem. All right. So we fixed some money income Y0. Then we did the utility maximization, found the point of tangency, found the optimal choices. And let's say at the end of it, the maximized utility was U0. So Y0 and U0 are specific numbers. Y0 could be 100 rupees, U0 could be 25, what have you. Okay, so these are specific values. Now, let's say in the dual problem, we take this U0, right? The value we got by maximizing utility in the other problem, given this fixed income level. Suppose I plug in that value into my constraint, right? So minimize expenditure subject to utility being no less than U0, this U0 that we got, right? Then what will be the minimized value of expenditure? Well, it's not hard to see that that has to be Y0. Okay, so if we fix the utility level at this U0 from the other problem, then the isocost line, which will achieve tangency, will correspond to the expenditure level of Y0, right? So in other words, U0 and Y0 is a pair. If we use this value in the constraint of this, if we use this income in the constraint of our utility maximization, we'll get this utility, right? And if we use this value in the constraint of our dual problem, then we'll get this expenditure, right? And there are several such pairs, utility and income pairs. And not only that, if we use U0, Y0, this pair in the constraints of these two problems, then basically it will be the same point of tangency will give us the solution. Right? And so the optimal choices in the two problems will be the same. All right. I'm not going to do a formal proof of this, but the logic is fairly kind of obvious, and you can try to sort of dot the I's and cross the T's for a formal proof. But I think from the picture and general intuition, it should be fairly obvious. So this is the duality kind of relationship that we will exploit to some extent. So here's the more general statement of the relevant mathematical result. So let's say fx and gx are increasing functions. And suppose we look at this problem, maximize fx subject to gx not exceeding some given number g star. And once we do the optimization, suppose we get the number f star. If you look at the dual problem, which is minimize gx subject to fx not exceeding f star, the answer we'll get is g star, that value which we used in the constraint of the other problem. Yes. So this is our uh, general duality result. So for the consumer's case, as I just discussed, the dual problem is this: expenditure minimization. And we have the same, so in terms of mathematical treatment, I showed you the picture, the diagram. In terms of mathematics, you can again write down the Lagrangian, for interior solutions, you get the sort of equality conditions and so on. And you'll get back that same tangency condition that MRS has to equal price ratio for every pair of goods. Okay. Now, the solutions to this dual problem, right? These values are called the Hicksian demand functions. Okay. So Hicksian demand functions too. So the solutions to the utility maximization give us Marshallian demand functions, and solutions to its dual gives us Hicksian demand functions. Let me just point out that Marshallian demand functions and Hicksian demand functions have different arguments. That's why they are different, right? Because they're coming from reverse problems, exercises. Both of them are functions of price vectors, right? But the Marshallian demand function was a function of income, because income was given and utility was being maximized. That's where the Marshallian functions came out of. In the Hicksian case, they're functions of utility, the utility target, right? Subject to which expenditure is being minimized. And the value function of this dual problem is called the expenditure function, right? Once we find the Hicksian demand functions or the optimal choices and plug that back into the utility function, plug that back into this function, P times X, right? We get the magnitude, the minimized value of this, and that is called expenditure function, right? Again, expenditure functions, because Hicksian demand functions are functions of prices and utility, so are expenditure functions. Okay. Now, given the kind of duality, the nature of duality that we discussed, and given this result, there are some duality-based properties that we can write down, some linkages between, say, Marshallian demand functions and Hicksian demand functions. So, or in other words, some linkages between the choice functions of the two problems, right? The original utility maximization problem and its dual, okay? So these first two equations are describe what is the relationship between the choice functions of the two problems, right? And the second two give us relationship between the value functions of the two problems, yes? And they follow basically from definition, they follow from this result, and also this observation which I did in the, that there are these pairs, right? This utility level and this income level are intimately connected, right? If you use one of them as a constraint in one of the functions, you get the other one as the maximized or minimized values, and vice versa. And once you use this pair in the constraints of the two problems, you get the same point of tangency as the solution, right? So that if we exploit that, so for example, I won't go through all of them, but this is one relationship between Marshallian and Hicksian demand functions. So what is VPY? It's if you fix the income at Y, right? So let's say Y and U are a conjugate pair, right? So meaning that that say U and Y are specific numbers, and if the income is fixed at y, maximized utility will be u, and if utility target is fixed at y, minimized income will be y. So they're a connected pair, right? So look at this. If you fix the money income at y, this is the maximized value of utility. And now if you put that value of utility in the Hickson demand function, you get back the Marshallian demand function for that income level y, right? So that is essentially restating this condition that the points of tangency are the same. It's the same solutions. Let's talk about some properties of the expenditure function. And this is the last step before we get to the heart of the matter, which is, as I said, testable implications. So many of these properties, don't even require elaborate proofs. They're quite obvious or intuitive. Let me go through some of them. The last two are the important ones, which will be useful for us as we move ahead. Okay. If nothing is consumed, this is the zero vector, right? It gives a certain level of utility. And of course, you can always reach that utility level for free, right? Right. Whatever utility you get from being a complete ascetic, not consuming anything at all, if the government takes that as a target, that utility level, you have to be taken to that utility level. The government doesn't have to buy anything for you, right? Okay. Some technical things like, expenditure functions will be continuous. The expenditure function is strictly increasing in U and unbounded above, right? That's pretty trivial. I'll leave it to you to think. I mean, it's really quite trivial. The expenditure function is increasing in prices, right? Why is that?
So, because cost increases
Yes.
of purchasing the same bundle if the price increases.
Right. So if the price of something goes up, right? So there's an initial set of prices. Anubhav, please switch off your video and audio. Thanks. So say there's a given set of prices, and there are some optimal choices and some expenditure is incurred after minimization. And then one of the prices goes up. Yes. If you continue to buy the same basket of goods for the consumer, of course, expenditure will increase. But typically, re-optimization will take place, right? If one of the prices goes up, then a different vector of goods will be purchased to reach the same level of utility. So then it's not immediately obvious that, expenditure has to go up. But the argument is that for every bundle, the cost is higher. For the optimal bundle, for non-optimal bundles, whenever one price goes up, every bundle is more costly. So whatever is optimum has to be more costly, right? The expenditure function is homogeneous of degree 1 in prices. Yes. That means if all the prices double, then the expenditure function will also double, right? The value of the expenditure function. So why is that? basically, if all the prices double and you continue to buy the same basket as before to reach the target level of utility, then expenditure will double. Okay. Problem is that maybe after all prices double, you may want to buy a different basket of goods, right? And then we are not sure whether expenditure will double or not, right? But then if you look at the optimality condition, right, margin MRS equals price ratio, when both all prices double, the price ratios don't change. So the same basket of good remains optimal after all the prices have gone up by the same factor, right? So therefore, if all prices double, you continue to buy the same basket of goods, and it's twice as costly as before. Okay, so these are all pretty simple, but let's get to the properties which are really going to take us to the next step. First is that the expenditure function is concave in prices. And the second is Shepard's lemma, right? Shepard's lemma tells us, like it's the corresponding version of Roy's identity for the dual problem, right? It says that here's the link between the value function of the problem and the choice function of the problem. If you know the value function or expenditure function, and if you take the derivative with respect to the ith price, that will give you the ith Higgs-Hindenburg function, right? I'll get to concavity in just a second. Can you guess which mathematical result we have to use to prove Shepard's lemma?
Envelope theorem.
Envelope theorem, right? It's absolutely straightforward, right? I'll leave it to you. I mean, it's a one-liner. The envelope theorem says that the derivative of the value function, namely here the expenditure function, will be given by derivative of the Lagrangian of the problem. So if you write down the Lagrangian and take its derivative, you'll get basically xi. Yeah. Okay. Let me prove concavity of the expenditure function. Yeah. And we are not going to use calculus. There's a more direct, straightforward way of proving concavity, which follows from the definition of expenditure minimization. So very quickly, let's look at the proof. So let's take, what do we have to prove for concavity? Okay, let's talk about concavity of a function for a moment. So just a little technical digression so that we understand concavity firmly, concavity and convexity of a function. So take the simplest single variable case, all right? And let me draw a concave function. Here's a concave function, yes. What is the standout feature of a concave function? It's that if you take 2 points, x1, x2, look at the relevant points on the graph. And if you join a straight line, that straight line will lie entirely below the function. If we had a convex function, it'll be exactly the opposite. Okay. Now, that is the very definition of concave and convex functions. Or well, before I get to that, let me backtrack. Okay, let's take this simple case, single variable case. What does it mean to say that, this straight line will lie below the graph in the case of concave functions, but will lie entirely above in the case of convex functions? Well, take any point in the middle of the x-axis, right? So let's say this is x bar, lambda x1 plus 1 minus lambda x2. It's some weighted average of the two initial points that we chose. Okay. If we take, okay, on the vertical axis, this is f of x1, the value of the function at x1, because I'm reading it off the graph, and this is f of x2. Okay. So if I took the weighted average of the functional values, one minus lambda f of x2, then that point can be read of the straight line. Okay. So this weighted average has this value, and that weighted average has this value. Okay. Basically, the x value and the functional value, they're linearly related like this, right? You can easily check that. So, okay, so if I evaluate the value of the function first at the points x1, x2, and then take a weighted average, the magnitude I'll get will be given by the height of the straight line. But if I did it in the reverse sequence, if I first took the weighted average of the x values and then plugged it into the function and evaluated it, that will be given by the height of the graph at this point. Okay, so this is given by this magnitude. Okay, so to say that the line lies below the graph of the function basically amounts to saying that this object is less than that. So if I take average first and then put it inside the function, then I get some higher magnitude than if I first put the x1s and x2s inside the function and then average it. Okay. This is basically the definition of a concave function, right? So the definition extends to cases where it's not a single variable function, but a multivariate function, right? Where these x1s, x2s are vectors, not just single numbers. And in the case of concave functions, this inequality will just be the opposite. It will be the other way around. Yes. So the very definition of concavity and convexity involves these inequalities, right? Now, you might ask that, well, okay, I like doing calculus. And so if we have a function f of x1, x2, x3, xn, and suppose it is indeed concave, that is, it satisfies this inequality definition of concavity, is there a calculus way in which I can describe it in terms of derivatives, right? What will have so for example, if the function is concave like this, all right, this inequality property has to be satisfied. But in terms of derivatives, we know that the second derivative has to be negative. Okay, so this inequality property and this second derivative property are connected for differentiable functions. They're identical. They lead to the same kind of function, same curvature property. So, so if I have a function like this, I know it's concave, that is to say it satisfies this inequality property. And I'm wondering, in terms of second derivatives, what can I say about this concave function, right? Since it's not a single variable function anymore, this is not sufficient, right? There has to be something more complex. So what is it? What is that condition? What is the analog of, f double prime being negative for single variable functions in the multivariate case? So I'm not going to prove things, but let me, again, in a recipe book approach, just give you what the analogous condition is. You construct the Hessian matrix. The Hessian matrix is the matrix of all the second derivatives of this function, right? So you have f11, okay, f12 to f1n, and here you have fn1, fnn. All right. So the analogous condition of our negative second derivative in the single variable case is that the Hessian matrix is negative semi-definite. Okay, what is called negative semi-definite. Now, what that turns out to be, what that means is that, you have all the principal minors of this matrix, right? So there's a submatrix, which is this. Then there's a second submatrix, which is the 2 by 2 thing. Then there's a third submatrix. So these are called the principal minors. The determinants of these are the principal minors, right? So principal minor 1, which is f11, which is f11, that has to be negative. Principal minor 2, which is f22, that has to be positive, and so on it goes, right? M3 has to be negative, and so on. Okay? So keep this in mind. A function is concave if either this inequality property is satisfied, and if it's a differential function, equivalently, if the Hessian matrix is negative semi-definite. Yeah. So what we are going to do for the expenditure?
So,
Yes. Yes.
so, so this is unconstrained optimization, the Hessian matrix condition, because in this we are talking about unconstrained, right? Or constrained optimization.
Yeah. It is unconstrained.
So are we? Am I audible, sir?
Yes.
Yeah. Okay.
What I discussed here
Okay,
is properties of functions. It has nothing to do, this per se has nothing to do with constrained or unconstrained optimization, right? These properties will become relevant when we discuss optimization as we were discussing. But this is a side note where I am just clarifying what does it mean for a function of many variables to be concave. All right?
Okay, sir. Thanks.
Yeah. Okay, so getting back to the slides, as I said, there's a claim here that the expenditure function is concave in prices, right? The way we can prove it is just show that the inequality definition of concave functions that I just described is satisfied, right? That's one way to show it. And that's what I've done here. So very quickly, let me go through the steps here. It's pretty simple. So let's say let's take two price vectors, P superscript 1 and P superscript 2. These are both price vectors. That's why they're in capital letters, right? They are a whole set of prices. And let's say the optimum quantity vectors are x1 and x2 respectively. So when price vector is P1, optimum choice is x1, and so on. Okay. Optimum in the sense of what? Optimum in the sense that it solves expenditure minimization. So these two inequalities follow from the fact that we have defined x1, x2 to be the optimal choices under those price vectors, right? So when the price vector is P1, if we choose x1, this will be the total expenditure. If we choose x bar, what is x? Sorry, I should have said what is x bar. So to prove concavity, we have to basically show that the expenditure, we have to look at expenditure at some averaged price vector like this, right? So P bar is an averaged price vector. And let's say the optimum choice there is X bar, right? When you move to this averaged price vector. Okay, now these two inequalities follow from definition, right? If the price vector is P1, X1 is less expensive, or at least no more expensive than X bar, because it is optimal under that price vector. When the price vector is a P2, X2 is no more expensive than anything else, less expensive than everything else. And so we can write this inequality. And now it's very simple. We just multiply both sides of the first inequality by lambda, both sides here by 1 minus lambda. So that gives you this inequality, right? It's a valid inequality, follows from the first two. And now if you look at it closely, on the right-hand side of this inequality, you basically have that average price vector P bar. So the right-hand side becomes P bar times X bar, right? Vector product. And on the left-hand side, and that vector product is essentially the expenditure at this average price vector. And on the left-hand side, you have this, right? So this is the inequality which defines concave functions. Yes. So the expenditure function satisfies the definition of concavity. And so it's concave. All right. Questions? Okay, let me move on.
Sir, how?
Yeah.
So how did we come to the expenditure function from that previous equation?
In this line.
Yes, sir.
The product of P1, X1, what is that? See, when the price vector is P1, optimum choice is X1, and this product is by definition, this product is what we were trying to minimize. So,
Yes, sir.
So that is precisely the minimized value of expenditure.
Okay.
That is the value that the expenditure function will take, right? For price vector P1, if you put in some other non-optimal vector, then you won't get the value of the expenditure function. It will get something bigger, right?
Okay, sir.
Sir, I had a question.
Yeah.
Sir, the properties of the expenditure function which we did just now. So the rest of the properties, sir, we have to do all of them.
In principle, you have to do everything. I mean, what do you mean whether you have to do all of them? Of course, I mean, nothing is irrelevant, right? Let's first learn the stuff. We can talk about exams and questions. Let me just say in general that, somebody asked it the other day that don't memorize stuff, all these things, just try to understand them. I've said this repeatedly. I won't sort of ask you straightforward proofs on this sort of material. I won't ask you, prove Shepard's lemma, prove the expenditure function is concave. I don't ask questions like that. I ask problem solving kind of questions where you have to sort of think on your feet to some extent, right? I'll say, okay, here's a utility maximum, here's a consumer's problem, here's a firm's problem, etc., etc. You can see plenty of examples in problem sets and so on, right? So I won't, like your undergraduate, write short notes on this, prove this result from the book, from the slides. That's not the kind of questions I ask, Okay, so you don't have to memorize stuff. That's absolutely a killer. I'm stressing it repeatedly. But you do have to understand, so just because I won't ask you the proof of Shepard's lemma or whatever does not mean that you don't have to understand these things and you can switch off, because the kind of logic that we are using here is the kind of logic which will help you solve problems. Okay, so there's no principle to lay down. Try to follow everything, understand everything, then solve the problems, and you'll get the hang of it. Solve the problem sets. So past exact questions.
Okay.
Sir,
Yeah. Yeah.
sir, if X bar is minimizing the expenditure, so P1 X bar should be less than equal to P1 X1. No?
Then what?
P1 X bar should be less than equal to.
X
Because
bar is
X bar is
minimizing.
minimizing.
Let me ask you this. You have to be, look, you have to be always careful with detail. X bar is minimizing expenditure when the same basket of goods does not minimize expenditure no matter what. It minimizes expenditure maybe for some price vector, but not for other price vectors. So when you say X bar is minimizing expenditure, it is when the price vector takes a specific form, namely P bar. X bar is the optimal choice when the price vector is P bar. If the price vector is something else, then X bar is not the optimal choice, right? So P bar X bar is the minimized expenditure when the price vector is P bar. That's why and P bar
Sir,
is.
in the above expression, in the above inequality, I'm saying the first inequality, P1 X1 should be greater than equal to P1 X bar, no? Because X1 is minimizing the cost for
That's what
P1
I've
price.
written. That's what I've written. I've only written, I mean, the only thing you can be uncomfortable with is that the inequality is weak. Is that what you're saying?
No, sir,
What?
I'm saying P1 X1 should be greater than equal to P1 X bar.
Why?
Because X bar is minimizing the expenditure.
That's what I'm telling you. X bar is minimizing expenditure when the price vector is P bar. X bar is not minimizing expenditure when the price vector is P1. When the price vector is P1, the optimal choice is X1. You have to pay attention to the detail. Okay, so so this is a kind of a centerpiece, right? The Slutsky equation. And what the, oh. So the Slutsky equation, how am I doing on time? Oh. So the Slutsky equation says that well, first, let me start sort of kind of in a technical way, that the slope of the Marshallian demand function, right? Ith Marshallian demand function, its slope with respect to the jth price. It can be written in this form with two terms. The first term is the corresponding slope of the Hessian demand function. All right? So slope of Marshallian demand function equals slope of Hessian demand function plus an extra term, which involves the slope of the Marshallian demand function with respect to income, right? Del xi, del y times xj. This first term is what is called the substitution effect, and the second term is what is called the income effect. Yes. Okay. How do we prove the Slutsky equation? We can have a very short proof using duality and so on, right? So as I said earlier, this is a relationship between Hessian and Marshallian demand functions. If I start with some fixed utility level U, evaluate what is the least costly way of reaching that utility U, give the consumer that amount of money, and let the consumer do utility maximization, I will get back the same utility level U, And Marshallian and Hicksian demand functions will coincide because we are looking at the same point of tangency for the two problems. So if you take this as a starting point, and this is true as this is an identity, it's true by definition. So then if you differentiate the two sides with respect to price Pj, you end up getting the Slutsky equation, right? So you can follow the steps. Let me get to the sort of more conceptual points. So I'll let you fill in these details and follow them yourselves. So that's the technical proof is fairly short using these duality kind of techniques. But what does it all mean, and why is it relevant? Okay, what does it mean? Let me, and again, those of you who have taken economics at the undergraduate level, you're familiar with the concept, should be familiar with the concept, but let me briefly, intuitively give an idea, drawing a picture, and then relate it to the maths. So take the simple two good case. Okay, so x2, x1, and initially you have some budget line, and you have a point of tangency. And then let's say the price of good one goes up. So we have a new budget line like this and a new point of tangency. Right. So the change in the consumption of good X1 is this amount, and the change in the consumption of good 2 is this amount, right? What the Slotsky equation does is that it takes this change and breaks it down into two parts, which are conceptually very important. So you have this new budget line after the price increase. And suppose we or the government decides to give the household or the consumer some compensation so that they don't, they remain at the old utility level, let's say U0, right? So you give some compensation so that, utility of the consumer does not fall. Of course, that means giving some extra income, right? And as the government gives some extra income, there's a parallel shift of the new budget line in the outward direction. And you have to continue till you hit a point of tangency here, right? So the original point was A. After the price increase, the new point is C. But if enough compensation is given to push the consumer back to the old indifference curve, then we will reach point B, okay? So this part of, so now we'll think of the effect of the price change on, let's say, the consumption of good one as consisting of these two parts, right? So if only the price has changed and the relative prices moved around, but the consumer's real income, if you will, did not fall, right? The consumer still was given extra money to remain at the same utility level, then she would cut down her consumption of X by this amount. So this is what is called the substitution effect. But in reality, no such compensation is given. And so this part of the change in consumption comes from the fact that the consumer's real income or purchasing power has gone down. And that is what is called the income effect. So mathematically, the two terms that we derived in the Slutsky equation capture these two things, the income and the substitution effects. Okay. Now, let me quickly plug it back, the power source. So let's get to the issue of what are the testable implications, as I said, right? The first two are pretty trivial, right? There has to be budget balancedness because, you know, all the income will be exhausted. There's no wastage. That's a straightforward implication of utility maximization. And the demand functions are homogeneous of degree 0. Let me get to the important thing. The expenditure function is negative semi-definite. So, sorry, the expenditure function is concave. That means this matrix, this Hessian matrix, is negative semi-definite, right? In the sense that I talked about. Now, we can convert this matrix of second derivatives of the expenditure function into a matrix of first derivatives of the Hessian demand functions. Why? Using what result? Let me backtrack. Let me go back to the result we proved that the expenditure function is concave, right? As I discussed earlier, if a differentiable function is concave, right? The calculus property that has to be satisfied, the properties of derivatives, is that the matrix of the second derivatives, the Hessian matrix of that function, has to be negative semi-definite. Its principal minors have to alternate in sign, right? Now, so this matrix is negative semi-definite due to concavity of the expenditure function. Now, this matrix is equivalent to this matrix, right? These are the second derivatives of the expenditure function. These are the first derivatives of the Hessian demand function. What allows me to go from this matrix to that matrix? Say that again.
Shepard's lemma.
Shepard's lemma, right? Shepard's lemma is exactly, that's why we proved it. Yes, Shepard's lemma. Shepard's lemma says that the first derivative of the expenditure function with respect to, let's say, the ith price gives us the ith Hessian demand function. So now if I differentiate both sides again with respect to Pj, then I'll get, you know, the cross partial with respect to I and j here on the right hand side will be equal to the derivative of the ith Hessian demand function. So Shepard's lemma. Now, so this matrix written in this form is negative semi-definite. That means the principal minors alternate in sign, right? That means, for example, that the very first derivative is negative, right? So slope of the Hessian demand function of the first good is negative, right? Or at least non-positive. And you can show from that matrix condition that all the diagonal elements have to be negative, right? So all the slopes of the various Hessian demand functions with respect to the price of that good itself will all have to be negative, right? Now, that's the main result that we can prove from this theory, right? Now, I advertised it as a testable implication. I said, okay, I'll show you what the testable implication of the theory is. And now I'm saying, okay, negative semi-definiteness of this matrix, one implication of which is that Hicksian demand functions are downward sloping with respect to the price of the good, not the price of another good, but with respect to the price of the good itself. Hicksian demand functions are downward sloping. Is that a testable implication? Can we verify or reject that claim by looking at market data?
Yes, sir.
Oh. We don't observe Hicksian demand functions, right? Consumers out there, they're not solving expenditure minimization subject to some target utility level. They're actually solving utility maximization. So the demand functions that we can see in the market, if we collect the data and estimate demand functions, they'll be Marshallian demand functions. They won't be Hicksian demand functions. So on the face of it, this would look like false advertisement that, I am telling you that these are the testable implications of the theory. In particular, part of the testable implication is that Hicksian demand functions are downward sloping. And then you will say, well, we don't observe Hicksian demand functions. So what have you given us? This is just useless, right? That's where the Slutsky equation comes in. Look at the Slutsky equation. Slope of Marshallian demand function is slope of Hicksian demand function plus the income slope of the Marshallian demand function. So take this to the other side, right? Take the second term to the left-hand side. So we can replace all the slopes of these Hicksian demand functions in this matrix by the corresponding slopes of the Marshallian demand functions as per the Slutsky equation, okay? And that is what ultimately makes this a testable implication. So now we can estimate all these demand functions from the market and check whether this matrix is indeed negative semi-definite, where after substituting all the Hicksian slopes with the Marshallian slopes, right? Now, the substitution effect is slope of the Hicksian demand function being negative basically means, if you go back to the Slutsky equation, that slope is nothing but the substitution effect, right? So our theory says that the substitution effect of a price change will always be negative. Sorry. This is the general Slutsky equation, right? Think of change in the price of the good itself. So replace J by I, the special case where J equal to I, right? So, so there, because all these diagonal elements are negative, right? That means when the price of the good itself changes, the substitution effect it creates is always negative. But the income effect can be negative or positive. Yes. If it's a normal good, then this derivative is positive, and then the second term will also be negative. So for normal goods, goods which are consumed in higher amounts at higher income levels, the entire effect is negative because both substitution and income effects are negative. But if it's an inferior good, right? If del xi, del y is negative, then the income effect turns out to be positive and the substitution effect is negative. And so in theory, it's possible that a large negative income effect coming from here dominates the substitution. A large sort of positive income effect here dominates the effect of the substitution effect. And then the slope of the Marshallian demand function with respect to its own price could be perverse. It could be positively sloped. Okay, so those are called Giffen goods. Yes. Okay. Can I just take a couple of minutes? Again, the time is you guys have another class now?
No, sir.
No, sir.
Tutorial.
I'll just wrap it up, okay?
No, sir.
So just just give me 2 or 3 minutes. Yeah. uh, so the so-called law of demand, which says that for any good, there's a negative relationship between the price of that good and the demand for the good. The law of demand is not firmly founded. Okay, this theoretical framework that we have built up does not give us the law of demand. Yes, in principle, demand curves can be positively sloped. That's what we are getting over here, right? For a large class of commodities, namely normal goods, the law of demand will be valid. Okay, but for inferior goods, the law of demand may not hold. Okay, so in those special cases, which are called Giffen goods, so what the classic example and where the name comes from is potatoes in Ireland in the early 20th century. So an economist called Robert Giffen did a study where he allegedly found that when potato prices went up, people bought more potatoes. Intuitively, what is the connection to all this maths and these diagrams and this income and substitution effect? Think of the Irish example. Ireland then was a very, very poor country, right? Ireland much later, last 10, 15 years has been a roaring economy. But back then it was one of the poorest countries in Europe.
Huh?
So a typical poor Irish household would survive on bread and potatoes. That will be their staple diet. And occasionally they'll have protein diets like meat and fish or something. A poor household, throughout the week, they eat bread and potatoes for 6 days, and they save up little amounts so that on Sunday they can have a more luxurious meal, like they can have meat. But then potatoes become more expensive, and for 6 days they are not able to save much. For the 6 days they have to eat potatoes. They're not rich. They can buy meat every day. So when it comes to Sunday, they find that they don't have enough savings to buy meat. But on Sunday they have to eat, so they can go and buy potatoes again and eat potatoes, right? So if you think about that story, you can see why in certain cases demand curves may be positively sloped. Yes. So that's what all this Slutsky equation and the results that we have proved tell us. Proves it formally that the law of demand, strictly speaking, will not hold, but it'll hold for normal goods. Yes. There may be other reasons why sometimes demand curves may be positively sloped. Yes. Let me give you 1 or 2 examples. So for example, demand for luxury cars like Lamborghinis, or very rich people buy these things. Suppose these Lamborghinis or Ferraris became much cheaper. They were like priced like your Honda Cities. Well, not Honda Cities, whatever. Suppose their price falls. It's conceivable that some people will be turned off by that. Some of the buyers, they will not buy. One of the reasons, these are display goods. Okay, they are sometimes called Veblen goods, after Thorsten Veblen, who wrote about conspicuous consumption of the rich. If people want to display wealth, if people want to advertise that they're very rich, okay, of course they can kind of take their bank statements and show it around, but that'll be very vulgar. So one way to do that is to buy expensive cars and watches, which people can see, and so the signal goes out that I'm rich. But if those goods become a little less expensive, then the signal is not so strong anymore, right? If even upper middle class people can afford these Ferraris and Lamborghinis, then the very rich may be looking for other ways to advertise their wealth. So that's called the Veblen effect, right? That some goods are bought to advertise wealth and richness and so on. So for Veblen goods, you can imagine demand curves to be positively sloped. That if price comes down, some people will stop buying it because it's not enough of an advertisement of their wealth. But in our framework, Veblen goods are not allowed because in our framework, goods they have intrinsic utility. They're bought for their intrinsic use value, not to signal something to the rest of society, right? So we're keeping out some of the fancy reasons why some kinds of exotic goods, like fancy cars, may have positively sloped demand curves. Even for sort of mundane goods like bread and potatoes, we can't, strictly speaking, derive the law of demand. Okay, so I've completed the theory, and there's a little bit of discussion left about some applications and some possible anomalies or shortcomings of the standard kind of textbook model. So I'll discuss that in the next class. And by this point, you should really get very much into the second problem set and solving those problems. Questions?
Sir, I just need a small clarification.
Say that again. Say that again.
Hello, sir. Am I audible?
Yes.
Sir, I'm saying that if in a Hessian matrix, if we are getting the first Hessian matrix value equal to 0, so will it still considered as negative semi-definite?
Again, it is, there's an issue of strict negative semi-definiteness versus weak, right? So if we just don't insist on strictness, some of these inequalities can be weak inequalities. Yeah.
So like it will be still a negative definite, but it will call up weak.
That's right. Yeah.
Okay, sir. Thanks.
Sir, can you tell me the intuitive reason behind the concavity of prices?
Behind the concavity of what?
Concavity of prices in expenditure function.
I've got this question before. I don't have a good intuition. If some of you can, I don't know why this. I don't have a good intuition. The proof is not very difficult. It's not very long or convoluted. You guys think about it. If you can come up with a nice intuitive way of explaining it, that'd be good. Some results sometimes, it's very hard to give intuition. I try for most things, and I'm not saying there's no way of, I'll just challenge you to sort of think about it and come up with something yourself and tell me about it.
Sir, I have a small doubt on the proof itself.
Okay.
So in the proof, are we assuming x bar to be greater than x1 and similarly
I'll
x
stop sharing,
bar?
okay? Sorry, I'll stop recording, I think. Yes, tell me.
So are we assuming x bar to be greater